So now we are going to understand, is it possible to crack the discrete log problem, DLP, of the secp256k1? There is a known scheme. There is a known scheme or an algorithm to actually solve this problem. So that is called baby step, giant step algorithm. So what is the purpose of the algorithm? Given the public key, where A is the private key, okay, n is the group order. If you just visit the specification, you will know what the number n is. So given the public key, can we find the private key A? So what we do is, first we find the square root of m and the ceiling of it. So if n is equal to 5, square root of n will be 2 point something, right? So we will choose m as 3. Okay, that's what ceiling means. And we initialize the hash table. Right? Hash table is nothing but a dictionary used in Python. The key will be the points on the elliptic curve, okay, that we compute. I initialize the variable which is called jg. So it is initialized to g. Okay, and at every step, I mean, yeah, this iteration should start from 1. Okay. At every step, I store that key in the hash table and the corresponding index, right? And yeah, when j is equal to 5, jg will be 5 times g. When j is equal to 100, it will be 100 times g, something like that. So these are called like baby steps. And the giant step, I compute c as negative m times g. So what is negative m times g in elliptic curve terminology? We first compute m times g, and the inverse is simply negating the y value. And that's how we find it. Right? Or else you can do you can simply compute n minus m first. So n minus m will be a positive number. So you simply multiply n minus m with g. So both will work. And I initialize this variable q with the public key point. Okay. At every iteration, I compute q as q plus c. If the computed value of q is already a key of which is stored in the hash table, then I take the value j out of that, corresponding value j out of that hash table, and I return this particular value as the key, as the private key. Okay. So why this works, why this algorithm should work, the reason is any A should be of this particular form, any private key should be of this particular form. And this A, it could be either less than square, it could either be less than m or A could be greater than m. In any case, we can write A as some quotient times m plus the remainder r. So that's here, so I will be the quotient, j will be the remainder. This is actually possible. You can actually verify that j will be strictly less than m, right? J actually satisfies the remainder property. Now the question is whether the secp256k1, like discrete log problem, is immune to this attack. This attack requires at least square root of n operations. So n is approximately equal to 10 to the power 77. Okay, it's slightly bigger than 10 to the power 77. Right. So it's a 256-bit number. If you convert it into the decimal form, it will be slightly bigger than 10 to the power 27. Okay. So square root of n is approximately equal to 10 to the power 38.5. Okay, let's assume that it's 10 to the power 38. Okay, for the benefit of doubt. Modern supercomputers can compute 10 to the power 18 flops, floating point operations per second. Which means modern computer requires at least 10 to the power 38 divided by 10 to the power 18 seconds. So that is equal to 10 to the power 20 seconds. It requires at least 10 to the power 20 seconds, and they also need to store the 10 to the power 20 times 32 or 64 public keys. Okay, the elliptic curve points. So that much memory you need, that much RAM you need in the first place. Let's assume that kind of RAM exists. Okay. So how long is 10 to the power 20 seconds? How many, is it a matter of days or matter of years or what? For that, let's open our Python calculator. Okay, let me remove this calculation first. let's start fresh. So duration will be, duration is equal to 10 to the power 20. How many seconds are there in a year? Okay, so let's call it seconds. Seconds in a year will be, in a year there are 265 days times 24 hours in a day times 60 minutes in an hour times 60 seconds in a minute. So let's do duration divided by seconds in year. Oh my god, it is, how many digits is this? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 digits. So it is like, it will take 3 times 10 to the power 13 years. Okay, that many, at least that many years with modern supercomputers to crack. And it has to run like all day for continuously that many years. Okay, that many years, not just days or seconds. So, this is how we improve our confidence in the Bitcoin network, right? We, as Bitcoiners, we simply don't trust. We try to understand, we try to verify for ourselves. There are like lots of things going on. Okay, attack from all sides. Even like as a Bitcoiner, you cannot simply trust the developers, okay, to push code and maintain the software for you. Is it very likely that those developers could be compromised, right? So you should be aware. You as a Bitcoiner doesn't have to accept every one of their updates. You can just read them, verify them. You can write your own code. You can fork the Bitcoin core, or there are many forks of the clients. You can verify the code. You can make modifications, right? But people are pushing for BIP 360, okay, to like add quantum computing, like quantum secure addresses, which are resistant to quantum attacks. Even recently, like Google announced that they have, their theoretical projection of whatever the research that they are currently doing can reduce the hardness of attacking RSA. Okay, that's not even about directly attacking the discrete-log problem used in secp256k1. Okay, for elliptic curve. Right, so there are like lots of FUDs going on. Okay, you need to keep a clear head and try to understand the technicalities clearly, and make your own decision. Your consensus matter. Okay, you can have a consensus, you can have a meaningful consensus only if you understand what is going on. I hope this course helps you to develop that understanding. I hope that you have already gained enough understanding, okay, to make more progress.